Welcome to Air Academy Associates series on using SPC XL. This video clip will introduce you to two of the most important and most commonly used hypothesis tests in process improvement, namely the T and the F tests. The T and the F tests are used when we have variables or continuous data like time or cycle time. And we will use the T test when we want to compare two averages or mean values. We will use the F test when we want to compare two standard deviations. A hypothesis test involves two statements or hypotheses. The null hypotheses, labeled H sub 0, will be as follows. The two population averages or standard deviations, if we're doing an F test, are equal. The alternative hypothesis states the two population averages or standard deviations, if we're doing an F test, are not equal. In a hypothesis test, we assume that H0 is true until proven differently. That is there enough evidence to conclude H1? And the beauty of such a test is that we get a number out. This number is called a p-value. The p-value is calculated from sample data and it provides the summary of the evidence. The p-value is a probability, which means it's a number between 0 and 1, and the p-value is the probability of concluding H1 falsely. That is, if we were to conclude H1, the p-value would be the probability that we would be wrong in concluding H1. Concluding H1 falsely is also called a type 1 error. So the p-value is the probability of making a type 1 error. And we don't want to make errors. We want the likelihood of making an error to be very, very small. So that's why we like and try to strive for small or low p-values. The old adage in hypothesis testing is this: if p is low, then ho must go. Well, what is ho? Ho is H sub 0, and that is we will reject H sub 0 and conclude H1 when the p-values are low. Well, that begs the question, how low is low? Well, fortunately, we have a rule of thumb for significance that states if the p-value for the test is less than 0.05, then we conclude that there is a significant difference in the average or the standard deviation depending on the test. And if the p-value is less than 0.05, SPC XL will print the p-value out in red. So it'll be right there in front of us, standing out. We won't be able to miss it. If the p-value is between 0.05 and 0.10, then there is a moderately significant difference. SPC XL will print these p-value ranges in blue. If the p-value is greater than 0.1, then we conclude there is no significant difference, or the test had an insignificant result. Now, if the p-value is low, the flip side of the p-value is 1 minus p-value. So 1 minus the p-value times 100 is the percent confidence we have in concluding H1. So if the p-value were 0.03, for example, then we would have 97% confidence in concluding H1. If the p-value were, for example, 0.08, then we would have 92% confidence including H1. Well, let's take an example and go to the software. The context for the example is turnaround times in a blood test laboratory where it's measured in minutes, and baseline data was collected with about 10 blood specimens and revealed about an average time at about 77 minutes. Now, this was the data right here that you see right here as far as the before the change made. Now, the team did make a change. They removed non-value added steps, improved the workflow, and then after the changes were made, they collected another 10 samples of data, and they got this data right here. So let's go to the software, and as we try to do almost always, we like to get a graphical depiction of the data first. For that, we're going to use a box plot, and then we will go to see if the differences in standard deviation and the differences in average turnaround are significant. So let's go to the software. I now brought up several data sets in this Microsoft Excel workbook, and the data we just looked at on turnaround times before and after a change was made is right here. I've just highlighted the data. We're going to go to analysis diagrams first, and get the box plot. I would like to see a graphical depiction of these data sets. We've already highlighted the data we collect next. Here's one area you have to be a little bit careful. Make sure you click data sets are in column, because we have multiple data sets. They're not in rows, they're in columns. We press next, and guess what? Here's our box plot for the before versus the after change data. And clearly there are differences. Differences clearly in what we think is the center point where those little pluses are, and probably differences in standard deviation or variation as well. However, we're going to see differences no matter, we're going to have sample to sample variation. So the question is, are these differences we see here due to sampling or random variation, or are they significant? And that's where the T and the F test can help us. So let's go back to the data, and let's go to the statistical tests. Go to sigma zone. In this case, all statistical hypotheses tests in SPC XL are in the analysis tools menu option. So let's do the F test first. And notice standard deviation is in parens there. It's a kindly reminder that the F test is going to be a test on a change or a shift in standard deviation. So we've already highlighted our data. We'll click through that. The data is in columns. This particular optional menu gives you a chance to do a two-sided test, which is the first option, or a one-sided test. The default is for the two-sided test, that is inequality, not equal to, rather than less than or greater than. And I would always use the two-sided test. It's a more conservative test. You'll get a better estimate on the p-values and a better estimate on the true confidence level if you are to conclude this alternative hypothesis that the variances or the standard deviations are not equal. So let's click OK, and here we get our ubiquitous p-value. Right there it is. It's 0.178. It's not red, it's not blue. What it's telling us is that the variances or the standard deviation, the variance is a statistical term which is the square of the standard deviation. So if the variances are different, the standard deviations are different also. And so 0.178 tells us what? Well, if you look down here, these are the two standard deviations of the two data sets, but these are the sample data sets, and the sample sizes are relatively small, 10 and 10, and the bottom line is there's not enough evidence here to conclude H1, not with high confidence. And so the bottom line here is the result of the F test shows us that there is not a significant difference between the standard deviations before we made the change and the standard deviation of the population data after we made the change. Let's go ahead and do the t-test. Well, let's go to Analysis Tool. This time we're going to choose the t-test. Again, in parens, you can see the word mean there. It's used to compare the mean values between data sets. That's what the t-test does. Let's click on that. We're using the same data set, so we can click right through here. The data is in columns, and we use the two-sided test. That is, we could error on either side, and this time we get a p-value of 0.001, and that indicates a significant result. And so 1 minus the p-value is 0.999 in percent. That means we can be 99.9% confident in what? In the H1 conclusion, that the means are not equal. They are different. As we suspected from the box plot, we thought the means would probably be different, and they were. We thought maybe the standard deviations would be different, but they were not. So in this case, in this data, the t-test result is significant, but the f-test result is not. Now let's take another data set. And the data sets, by the way, do not have to be the same sample size. And that in the previous example, they were. In this example, these are small data sets, and they are not the same sample size. These are LDL levels before and after I started taking Zocor. So I wanted to go in, look at the data before I took Zocor and after I took Zocor to see if the LDL levels are different. So as before, we come up and we get a quick look at the box plot of this data. We've highlighted the data. The data sets in two columns. We click next, and there is our box plot before and after. Now this is before and after Zocor. So it looks like the variation is pretty much the same. We will do the F-test to confirm that. It also looks like the mean values could be quite different. So let's check that out with the T and the F test. Let's do the F test first to see if there's a significant difference in variation. We come to the analysis tools, we go to F test. And F test is for standard deviation. We have our data highlighted. I click OK. Our data is in columns, not rows. We are going to do the strongest test, that is the two-sided test, the inequality and the alternative hypothesis. And sure enough, as the box plot kind of told us, we're not seeing a significant difference in standard deviation. P-value is 0.865. The two standard deviations under question are 7.6 and 8.5. No significant difference there. Let's go ahead and do the t-test here. Okay, we come up here. The data is still highlighted. We go to t-test. Click on that. That's the data, all right. The data is in columns, and we want the strong test. That is the alternative hypothesis of inequality. And in this case, we get, can you believe it or not, a red p-value. There it is. It's 0.000. So in this Zocor data also, I can be almost 100% confident, 0.999. It only gives us values to 3 places to the right of the decimal. I can be 100% confident that Zocor is doing a pretty doggone good job for me. That is, the difference between 145 reading on LDLs down to about 119 reading is significant. It's saying that that change would not happen by chance. And guess what? We did. We took Zocor between the two sets of the data, or started Zocor between the two sets of data. So the result of this Zocor data says that there's no significant difference in the variation or the standard deviations of the two data sets, but there is a significant difference in the means. So let's take one more data set, and you can use a t-test and an f-test when you have more than 2 data sets. In this case, we have 5 data sets, 5 different facilities. We've taken 15 data points on the appointment times for veterans to get an appointment. And basically we have 5 different facilities, and the sample sizes are the same. They're still not great. They're 15s. 15 is not a big sample size. But let's go ahead and get the analysis diagrams, the box plot. So we get the box plot, and the data is in columns. We say next, and sure enough, there's one of these facilities that kind of looks different from the other 4, and it's facility 3. Now the variation, as we look at the top to bottoms from the X's on each of the 4 or 5 data sets, don't appear to be a whole lot different, but the middle of this data set certainly appears to be different than the other guys. Let's check it out for significance by going to the analysis tools and doing an F-test. The F-test is for the standard deviation or the spread in the data. And now this might look a little complex at first because now we're getting a matrix. That's why the word matrix shows up in the analysis tools option for F-test and T-test. We are now doing 10 individual T-tests because we have 5 facilities and we're comparing every 2 of them. And for example, that p-value right there, 0.923, is the p-value when we get a comparison between facility 1 and facility 2. Between facility 1 and facility 3, we have a 0.57. We see no red values or blue values here. There are no significant differences between these 5 facilities. Now, let's go ahead and do the t-test. See what we get when we do the analysis tool t-test. And here's what I meant by the word matrix. When you have more than 2 data sets that you're comparing, you will get a matrix. In this case, we have 5, and we're doing the t-test now for shifts or changes in the mean. And we're data still in columns, and now we're seeing something where we're getting some red p-values. And guess where the red p-values are occurring? Between facility 1 and facility 3. Very small p-value, 0.0000. Between facility 2 and facility 3. And then between facility 3 and facility 4 is this p-value. And between facility 3 and facility 5 is this p-value. And in fact, every place where we see a red p-value, it is associated with facility 3. Well, guess what? We have no red anywhere else. That's not a real surprise because kind of the box plot was telling us that this guy is different than each of the other four, and amongst the other four, there's not a whole lot of difference. So that, folks, is what we present on the concept and the statistical hypothesis test called a t-test and an f-test. You can do it for more than 2 groups of data. The last one was for 5 groups of data, 5 facilities, but the more common one is to do it with 2 different groups. So the f-test and the t-test are very powerful tools to show you differences between before and after improvement, as well as other different comparisons you'd like to make as well. So I hope you enjoyed this presentation on the t-test and the f-test. Thank you for joining us.